Okay, so I'm Manuel Moreira. So thanks for this useful introduction. I'm going to talk about primordial reservoir. First, I have to say that we come back to a cute French accent, so it will be a second talk with a cute French accent for geochemistry. Anyway, after the Montana accent, it's maybe a kind of fresh air for you. The second important thing you have to know about the talk, it will be only 2 or 3 minutes now, because 2/3 of my talk was already done by Matthew Jackson just before, so it will be very short. Anyway, I'll try to speak slowly to keep people busy for 20 minutes. I'm going to talk about primordial reservoir, and I'm going to speak about how to keep this reservoir for 4.5 billion years, 4.5 billion years in the deep Earth. And the tool I'm going to use today is, in fact, the atmosphere mantle system. So we had some talks about the crust mantle systems. I'm going to talk about atmosphere mantle system, and I'm going to use the noble gases for that. And the other stuff you have to know about my talk is I won't present fancy cartoon as we have already seen. I'm fed up of the LVZZ and stuff like that. So it will be a geochemical point of view of mantle geochemistry. Anyway, what I'm going to do now is to study the mantle atmosphere system. When did the mantle degas? Is degassing complete? We can say also that do we have a primordial or primitive undegassed reservoir in the deep Earth? And if so, for how long did we preserve it in the deep mantle? So we'll see today it's probably something like 4.4 billion years. The question will be where it is. So that's probably what we have to discuss after the talk at the end of the day. So where it is. Is it in the melt pocket in the deep magma ocean left over or something like that? So I'm not going to give you the answer because I don't have the answer anyway. So, but we have some clue where it can be. So for people who are not geochemists, I'm going to give you a quick presentation of isotope geochemistry. Made simple, especially for my friend Edward Kamensky, who seems to have problems to understand isotope geochemistry. Anyway, a radiogenic isotope ratio reflects a chemical fractionation and time. That's the only thing you have to know, in fact, basically. Radiogenic isotope ratio we measure in the lab, it's just the result of few billion year integration of a chemical fractionation. And what is a chemical fractionation? It's just a translation to elemental chemistry of a geological event, such as core formation, melting, crystallization, degassing. That's the one we are looking at today. And we have other isotopic ratio I'm not going to use for the talk, which are the stable isotopic ratio. And stable isotopic ratio are fractionating during physical processes or chemical processes. But this is negligible for what I'm going to talk today. I'm going to talk about radiogenic isotopes. A second slide for non-geochemists is this slide, where radiogenic is in fact a ratio of a daughter, called here from the French staff, fils anyway. F is daughter, S is a stable isotope for reference, and P is a parent, which is a radioactive isotopes. So F is a radiogenic isotopes. Isotopic ratio is F over S. A chemical ratio named mu. It's why sometimes you find the I mu ratio. This is uranium-lead ratio, but here it will be only for iodine xenon or uranium helium. So mu is a chemical ratio, is a parent over a stable ratio. So it's rubidium over strontium, uranium over lead, iodine over xenon, etc., etc. You have only one equation, which is this radiogenic production. R, a ratio, isotopic ratio, R is primordial ratio plus a chemical ratio plus time, multiplied by time. That's the only thing we have to know. You can also look at the picture here, mu versus time. What is a chemical fractionation? A chemical fractionation is just a partitioning of the two elements between two reservoirs. It can be the core, it can be the silicate earth, it can be the atmosphere, it can be the mantle. So here you have a chemical fractionation which increases in this picture the mu ratio in one reservoir and decrease the ratio in the other reservoir. So it can be the core and the mantle, it can be the atmosphere and the mantle. If you have time, you can produce radiogenic ratio, and if you are now in the lab, you can measure the isotopic ratio and try to get back to the time of the chemical fractionation. A more complex story can happen for short life radiogenic isotopes, such as iodine-129, or the one we have seen in the first talk, the 142 samarium, for example. You have exactly the same process, except you need to do a process very early if you want to be able to measure something in the lab. Of course, we have error bars due to very old instruments, so we need more beautiful and fancy and expensive new instruments anyway to decrease the error bar. But you don't care because you have no money anymore. Yeah, anyway. If you want, why I'm saying that is, in fact, the precision you have will control the half-life or the dead time of the isotopes. Basically, what we usually say is after 10 half-life, the system is blind, so we cannot measure it. So if we measure something, the process has to be much earlier than the 10 times the half-lives, okay? But basically, it's exactly the same process. It just has to be early to be seen, okay? If it happens after, but we cannot see it. So the tool I'm going to use today is the noble gas family. And so noble gases are gases from a single family. This is the last column of the periodic table. So you have to learn all the name of the isotopes here. I will ask questions during the non-coffee break. Okay, so we have a family of 5 members: helium, neon, argon, krypton, and xenon. It's a very cool and good tool because you have both radiogenic isotopes like argon 40, iodine 129 gives xenon 129. We have helium 4, we have helium 3, so we have a lot of isotopes to play with. We have also non-radiogenic isotopes, such as neon 20, neon 22, which are considered as stable isotopes, so we can use also the noble gases to understand the physical processes in the solar nebula, for example. So, but I'm not going to use all the isotopes today. I'm going only to use 4 or 5, which is not bad, in fact. I'm going to use the helium, helium 4, helium 3. Helium 4 is radiogenic. This is the daughter of uranium and thorium. Helium 3 is the primordial isotopes. The interesting thing with helium is it can leave the atmosphere. So if you degas helium, you are sure it cannot be injected back by subduction because it has left the atmosphere to the space. We use the neon. Also, I will show you why. Neon is basically the brother of helium. We are using argon because argon 0 during Earth formation was 0. Argon is purely radiogenic, deriving from the potassium 40. And finally, to get access to primordial degassing, we use the xenon isotopic system with a half-life of 17 million years. The big problem we have with noble gases is we don't know what is the primordial composition of noble gases on Earth. This simple image here gives you 2 isotopic ratio, one for xenon, one for argon, one for krypton. And we can see in this image that all the mantle and the atmosphere are here, meteorites are here, and there is no way to pass from here to here in a simple way. So we are sure that the Earth was not chondritic for xenon. We don't know why. We don't know how we produce cis and member named phase Q, which is a carbonaceous component trapped in meteorites. We don't know, but what we know is the Earth is not chondritic. This is similar maybe to the neodymium. I will come back later on that. So we have some evidence that the atmosphere was degassed from the mantle, or at least part of the atmosphere derives from degassing of the mantle. As I said, argon is purely radiogenic. We have 1% argon in the atmosphere. Potassium is a lithophile element, so it was in the mantle of the Earth. So if it's now in the atmosphere, that means atmosphere was degassed from the mantle. Another argument is that the non-radiogenic isotope ratio of the xenon are similar in the mantle and in the atmosphere, which means probably these two processes are linked and that the atmosphere was degassed from the mantle. And then if we take a ship and take some seawater and measure the helium-3, you can see you have some helium-3 coming from the mantle above mid-oceanic ridges, which means that the mantle is still degassing. So some evidence that Earth is not completely degassed, that we have somewhere in the deep mantle, I don't know where, it's probably in the plume source, in the OIB source. It's very deep probably, but I don't know the volume, and I don't know where it is exactly. But what we know is we need a reservoir that is not degassed. The first argument made by Claude Allègre and Hal Hoffman was a co-author in 1995. It's what we call the argon budget. We know basically the potassium content of the Earth. It's derived from the uranium content of the carbonaceous chondrite or unstable chondrite or whatever chondrite you are using. But you can use the uranium, which is a refractory element, to get the potassium content of the Earth. And then if you have the potassium, you know how much argon-40 you have produced in 4.5 billion years. And then you remove what you have in the atmosphere, what you have in the upper mantle, and then you can derive that 50% of, between 50 and 60% of the argon is still in the mantle. It's still in the lower mantle. I don't know where. I don't know where it is. I have some ideas, but it's probably in the deep mantle. I don't know the volume of the reservoir. So you think I don't know anything, but I know some stuff. It depends. You can also use unstatile chondrites, and you get lower uraniums or lower potassium. So you have less argon-40 in the mantle, but you still have 20% of the argon, which is not degassed, and still in the lower mantle. So now we are back to the helium isotopic ratios. Matt Jackson has already shown some 3-4 ratio. Because I don't want you to be confused, I'm using the 4 helium-3 ratio, which is the opposite of the 3 helium-4 helium ratio. But why I'm using it is because helium-4 is a radiogenic isotope. So in my first slide, I was showing the parent or the daughter versus the stable ratio. So I'm still using it. It's basically the same thing as Matthew has said, is that most OIBs have lower 4-3 ratio or higher 3-4 ratio than mid-oceanic ridge basals. And a classical interpretation will be this very simple diagram where you have the 4 helium-3 ratio versus the time. And very basically, as we have said in the second slide, you have an evolution in a closed system of a mantle, a bulk Earth. And if you have a degassing, you increase the mu ratio, which is the thorium-uranium over helium-3, because you have lost the helium-3. And then, if you let the time to produce radiogenic helium-4, you will increase the helium-4 over helium-3 ratio in the degas reservoir. But the non-degas reservoir will be more primitive than the degas reservoir. So OIB are here, high helium-3-4 ratio, low 4-3 helium ratio, and the more is degassed, and OIB source seems to be not degassed. Now we are going to the neon, which is exactly the same thing, more complicated because we have 3 isotopes. But basically, you have to look at only the x-axis, which is the 21-22 neon ratio. And again, 21 neon is a brother of helium-4. So it's exactly the same way of thinking. When you degas, you increase the 21-22 neon ratio because you have less 22 neon ratio. And for the people who didn't understood yet, this is a very simple cartoon. If you have someone rich enough in the world to give 10 euros to everybody on Earth, if he gives me 10 euros, my salary will increase by a factor of 2. Or more or less. If you give the same amount of money to Bill Gates, of course, he won't see it. This is the same thing with the neon. If you have a neon 22 rich reservoir, you are rich. Even if you produce 21 neon, you won't see anything. Okay? You will keep your primordial signature. But if you are degassed, you will see more 21 neon. That's it. That doesn't mean you produce more 21 neon in this reservoir or in this reservoir. It's just that it's degassed, so you see more input of 21 neon. So we are sure now that this simple cartoon here, which is YBs versus mid-oceanic rich basalt, it's just a demonstration in the same way as helium that we have a primordial reservoir somewhere in the deep Earth. And I will come to a slide, the next slide after that. Is it primordial? It is not. That's the discussion we will have. But if we estimate, so the primordial mantle was close to the value of B. That's the chondritic composition or solar composition, whatever. So neon 21 will increase the ratio to the right. But you can estimate the age necessary to produce here the Galapagos value here or the Iceland value here, starting from B. So this is the value delta I'm using here versus time. And if you estimate an age, a model age, it's not really an age, it's a model age, for any kind of differentiation process that could have happened in any case, you get age of 4.42 billion years. So this reservoir has to be at least 4.4 billion years. So now we are back to a quick and fun cartoon I have made the other day. I told you that I don't want to use fancy cartoons, so I'm using beautiful boxes taken from the Labros et al. Model, where you have a magma ocean that crystallized by the middle. So here you have molten rocks. So you have a magma ocean at the surface, and you have molten rocks at the bottom of the mantle. And you start to crystallize by the middle, and you go up to the surface. What is important in this very simple cartoon is that this reservoir will be degassed very easily because it is at the surface. It's molten, but it is at the surface, so it is degassed. This reservoir is melted. It's a melt, but it's not at the surface, so it cannot be degassed. Gas has to stay where they are. They can diffuse probably a little, but they stay here. They cannot get to the surface. Degassing, it's just a surface process. And then if you crystallize, you keep some primordial gases here because it's not the gas. And whatever you do here, I mean, you crystallize dense crystals that can sink in the mantle, at the base of the mantle. You can keep some molten part of the mantle here. This part is processed. It has been molten, it has been melted, crystallized, but it's still undegassed, so it's still primordial for noble gases. So Stefan did a talk yesterday where he changed the position of the green reservoir. So I did another slide with a dense crystal reservoir at the bottom of the mantle. Of course, for me, it's exactly the same thing. I don't care. It can be at the bottom of the mantle. It can be in a sandwich between the degassed mantle. or the core, for me, it's not important. And next year, I think Stefan will produce a cartoon like that. Again, it will be exactly the same thing. I don't care. This is a primordial reservoir because it's not degassed. We'll see next year. Another example of what I want to say is that you can have a degassed reservoir, an undegassed reservoir. That doesn't mean it's primordial for lithophile elements. This is a famous strontium neodymium diagram where you have the more OIBs, continental crust here, and we have seen with the Maud's talk that we have a debate about the Earth being non-chondritic or chondritic for samarium neodymium ratio. Here, this is a cartoon by Caro and Bourdon, where the high helium 3-4 ratio, the low helium 4-3 ratio hotspots, the big hotspots like Iceland, Galapagos, or Reunion Island, they are somewhere here. They are not chondritic for samarium neodymium ratio. That doesn't mean they cannot be primordial. You can have fractionation between calcium perovskite, magnesium perovskite. Noble gases probably don't care about that because they can diffuse. They are inert chemically, so they don't care if you have calcium or magnesium perovskite. So the fractionation that we are looking at here for neodymium, it's completely different from the fractionation we are dealing with for helium and neon and argon also. So it's completely different. That means just this reservoir was not degassed. It may have crystallized some fancy phases or something like that. It's not degassed. So we finish with the iodine xenon systematics in the mantle. This is a 129 xenon over 130 xenon versus time. So remember, 129 xenon is a short life isotope decaying in 17 million years. So I did a quick calculation to produce the blue curve here, which will be the bulk Earth, a non-degassed Earth, a theoretical or not Earth. And if you degas the atmosphere very early, iodine is a lithophile element. It's not a volatile element, so it stays in the mantle. So you don't have iodine in the atmosphere, so you don't produce 129 xenon in the atmosphere. So you freeze the composition of the mantle when it was degassed. On the other hand, you have a fractionation, so you increase the iodine xenon ratio in the degassed mantle, so you will produce an excess of 129 xenon in a degassed mantle. And you can see here that the degassed mantle has radiogenic 129, undegassed reservoir will be at the middle, and atmosphere will be unradiogenic. That's because it's early degassing. If you do the degassing at 1 billion years here, of course, the three reservoirs will be identicals. And if you look at few, so this is very hard experiments to do because we have only something like 10⁻3, 10⁻4 ppt of xenon in mantle rocks. So it's very not precise. We need glasses sample. We need to be good, like me. No, kidding. No, not so kidding. Anyway, we need to, it's very hard. So we have only 3 to 4. Alain de Libera is calling. I don't know who is this guy, but we need to, this is very hard experiment, very precise, very hard. We need fresh samples. We have atmospheric contamination issues. Anyway, we get 3 hotspots, more than 3 samples, but 3 hotspots. It's Hawaii with the low E cement, Iceland, and Galapagos samples. And you can see that the OIBs are more radiogenic than the atmosphere, but much less radiogenic than the Moore reservoir. And that means only this scenario was probably the good one, and that we had the fractionation very early in the Earth history. And the other thing we have to learn from this figure is they are not mixed during geological time. They are preserved, isolated during 4.4 billion years. Otherwise, the composition will be the same because now they are stable isotopes. So if you mix these two reservoirs, you get a composition that will be identical. The compositions are different, so the reservoirs are isolated since 4.4 billion years. So we use this kind of systematics to try to get ages for degassing. So this is a very simple degassing model of the Earth, where here this is a stable isotope, so it will be helium-3. It can be argon-36, it can be 130 xenon, so this is unradiogenic isotopes. And the very basic model says that degassing is very quick in less than 100 million years, and then you have the tectonic regime by degassing of the mantle, like to the morb now. But we have something like 95% of the mantle that was degassed probably during the magma ocean stage. Okay? So basically, we always have the same age, 4.4 billion years. This is the same age as the core formation. So probably this is linked to the magma ocean stage. So no surprise. What we learned today is that this mantle was degassed, but we still have somewhere in the deep mantle a primordial reservoir. So my first conclusion slide is we have evidence that atmosphere was degassed from the mantle, probably during the first 100 million years, and then it's still degassing, but at much lower rate. Morb source is degassed. This is upper mantle, this is more than the upper mantle, I don't know, but morb source is degassed. We still have a deep reservoir sampled by oceanic island basalt, probably through mantle plumes, that is rich in primordial helium, neon, and radiogenic argon and xenon. It might be not primitive in the sense of lithophile elements. I mean, samarium neodymium could have been fractionated, but it's not degassed because it was deep in the mantle. To degass, you need to be close to the surface. My second conclusion slide on the last slide is that the xenon 129/130 ratio suggests that the morb and OIB source are isolated since 4.4 billion years. We don't know, so I come back to what I don't know is, I don't know the exact volume of this undegassed reservoir because we don't know from what we were starting from. We don't know the initial of the primordial composition in terms of abundances because they are very volatile elements, so we don't know what was the initial concentration of the xenon. Old-fashioned way of thinking was the undegassed reservoir is a lower mantle. I don't know if it will be the discussion today, probably. It's probably in the lower mantle. I don't know if it is all the lower mantle. It's probably located in piles at the bottom of the mantle, if we believe in Labros et al. Or Coltis et al. Recent papers. It also provides constraints on the magma ocean. It cannot have been a very vigorous convection because otherwise everything will be degassed, even if it was at the bottom of the mantle. If the convection was so active at that time, everything would have been degassed, which is not the case. Core is unlikely because noble gases are not siderophile elements. Anyway, I'm done. Thank you.